Hi, everyone. We're going to start Chapter 8 with matrices and determinants. And we're going to see a lot of this material in, well, your linear algebra class, Math 254, which is a very popular class. Many students take it, even some non-STEM people. So Section 8.1 will cover matrices, what they are. Normally, I'd play a commercial for the Keanu Reeves films, but we'll look at matrices. And in this section, we'll relate them to the systems of linear equations that we were talking about in Chapter 7. In fact, we're going to build up to 3 equations in 3 unknowns. So first off, what is a matrix? A matrix is the singular form. Matrices is the plural. So again, the Keanu Reeves films might be the matrices. A matrix is basically an organized box or array of numbers, or maybe other expressions like e to the x or sine of x. In this chapter, we will typically assume that our matrices contain only numbers, although on the homework, you will see some exceptions. So for example, this is a matrix, and we use brackets here, large brackets, to block off a matrix, the entries of the matrix. These entries are also called elements. This particular matrix consists of 6 entries or elements. You see here that this matrix has 2 rows and 3 columns. So we say that this matrix has size 2 by 3 because it has 2 rows and 3 columns. In general, we say that a matrix is M by N, where M is the number of rows and N is the number of columns. We never switch these. And such a matrix would have Mn entries. So for example, a 5 by 10 matrix would have 50 entries. That's something you probably won't have to write out in a math class, but a math problem could hint at it, and you might use some general notation. So as another example, some of our favorite matrices are square matrices. A square matrix is basically an n by n matrix, where m equals n. I'll type this. An n by n matrix, that is where m equals n, where the number of rows equals the number of columns. So for example, this here is a 2 by 2 square matrix, or an order 2 square matrix. The bold-faced entries here lie on what's called the main diagonal. It extends from the upper left to the lower right. Every square matrix has a main diagonal, and we're going to see that's very important later on in this section. In a 2 by 2 matrix, the other diagonal, going from upper right to lower left, is called the skew diagonal. And I'll also mention that diagonal later on when we discuss determinants. A determinant is a number we relate to this kind of matrix. So how can we apply matrices to a system of linear equations? And in Math 254, you might see this kind of system, where we have a system of 2 linear equations in 3 unknowns. In our class, I won't really do this to you. I'll generally give you a square system, a system of n linear equations in n unknowns. But in Math 254, you might have this kind of non-square system, 2 linear equations in 3 unknowns, say, x, y, and z. By the way, I highly suggest you cross your z's when you write them on a piece of paper. Why? Because in Math 252, Calculus 3, or in linear algebra, Math 254, many students mix up their z's and their 2's. And I've taken off points because students mix up their z's and their 2's. So please don't mix them up. And I do suggest you cross your z's. By the way, I also recommend you curl your t's, give them tails, so you don't confuse them with plus signs. That's also an error I see, students mixing symbols up. And it's a shame to lose points that way. Students don't like that. They don't like losing points, especially because of silly mix-ups like these. Okay, now what's the idea behind writing an augmented matrix? I say augmented because we're also going to consider the right-hand sides here. Now, one benefit to an augmented matrix when it comes to solving systems is that we don't have to keep writing X, Y, and Z. So when you were solving systems before, if you didn't like having to manipulate X, Y, and Z all the time, if you really like numbers, then matrix solutions are the solution for you. If you really like numbers and you don't like variables so much, letters, then you may well want to work with matrices. Now, sometimes if these equations are written in kind of a strange way, then it's good to rewrite them. And to write them in what we could call a standard form, okay? Basically, something like of the form ax plus by plus cz equals a number. When we prep ourselves for setting up the augmented matrix, we often like to start off by writing an equation like this, even if some terms are missing. So look at this form for this equation here. Notice that all the variable terms are on the left side in alphabetical order. The x term, then the y term, then the z term. Later on in linear algebra, you try to get more professional because in principle, you could have more than 26 unknowns in theory. So you might write your unknowns or variables as x sub 1, x sub 2, x sub 3, and so forth. In principle, you could go to x sub 1,000 or whatever. And sometimes you could be asked theory questions where you might have to consider 1,000 unknowns or variables. And you may not be able to list them all out explicitly. Oh, by the way, if you have x, y, and z, if you need a fourth unknown, a lot of books wrap back to w, and I realize that might be confusing for people. And if this is confusing, then you really should start doing this form with the numbered subscripts, if you have a choice. There's only one constant term, and it's on the right side. So this number over here, it could be 0 or not. If this is a 0, then we call this a homogeneous equation. And also in a system, in this group of equations, it's helpful to line up the like terms vertically. And in fact, this was helpful back in the addition or elimination method back in chapter 7. So the system that I showed you up here, it's good to line up the x terms, line up the y terms, even a missing space for this missing y term, line up the z terms, line up the constant terms. So something like this. Now, as a challenge to you, try to write the augmented matrix. You're going to write the coefficients for x in the first column, the coefficients for y in the second column, the coefficients for z, notice I'm crossing my z, in the third column, and put the right-hand side, which is kind of like a vector. It's like a 1x2 vector here. Put the right-hand side over here, consisting of these two right-hand sides. But be careful. You're writing down coefficients, and you may well make a mistake. But I'll give you a shot to try to get this right. 20 seconds, go. Let's see if you made any errors. You know, it might actually be helpful to write these in. And in fact, as you solve a problem, you might want to write these missing coefficients and terms in. Over here, the plus z means plus 1z, not plus 0z. See, a lot of students look at this quickly and they see a blank here. Oh, I see a blank here. So their brain sometimes instinctively will say, oh, I guess I put a 0. I see a blank. No, the implied coefficient is a 1. So the thing is, if you tend to write things down quickly, you might really benefit from rewriting the system. Because if you tend to grab things that you see, right, then you might want to use this kind of form. Put plus 1z here. So you make sure you don't put a 0 up here. Over here, we have the negative 2x in the second equation, missing term. There's a blank spot there. That corresponds to the missing term, plus or minus 0y. That 0 helps. You can put a 0 here in the middle bottom. Again, over here, that's not a 0. What's the coefficient? It's a negative 1z. So it may be a good idea, especially if you tend to grab pieces here to form your augmented matrix, it may be a good idea to insert coefficients of plus or minus 1 and 0. It's not necessary, but on the homework, as you practice on the homework, if you find that you mess up your augmented matrix without prepping this thing properly, then prep it properly. So part of the challenge here is knowing how much you have to prep your system in order to get the correct augmented matrix. To be safe, go all the way. Line up your like terms, put in missing coefficients and missing terms. Here's the answer. And by the way, if you're going to read these off directly, I know that many people are inclined to read these off equation by equation, and maybe that is better for some people. Let's look up here. Some people might think, oh, maybe I can read these off equation by equation, and maybe some people work better that way. But especially if you have it in this form here, where you put in the missing coefficients, it may actually be better to look at things column by column. Because then I think you're less likely to interpret like a 0 here, for example. All right, column by column. The column for x coefficients, 3 and negative 2. The column for y coefficients, 2 and 0. A lot of people miss that. The coefficients for z, 1 and negative 1. The right-hand sides, 0 and 3. Overall, what size is this matrix if you ignore the slash over here? Overall, this matrix is 2 by 4. What size is the coefficient matrix? That's 2 by 3. So because the coefficient matrix is not square, this is not a square system. It's not n linear equations in n unknowns. We don't see these so often in our class, but in Math 254, yes, you see these a lot, non-square systems. I can tell you right now that this system will not have one unique solution. The coefficient matrix consists of these coefficients to the left of this slash. The slash here corresponds to kind of these equal signs that separates these variable terms from the constant terms. The constant terms here on the right sides make up the right-hand side, the RHS. And you can kind of think of this as a vector or a thin matrix. It's like a vector. Or you could think of it as a 2 by 1 matrix. Sometimes we look at it one way, sometimes the other. Together, the coefficient matrix and the right-hand side make up the augmented matrix. I put a slash here to separate the coefficient matrix and the right-hand side. I know that Larson, for example, does not put this slash because he's afraid that when people perform operations, they forget to perform them on the right-hand side as well. That's up to you. If you tend to ignore the right-hand sides, maybe you're better off without the slash. I won't mark you off if you ignore it. Some authors do. Again, it may be faster for you to consider things column by column to retain accuracy. Why do we do this? One reason, the augmented matrix is an efficient representation of a system of linear equations, although the names of the variables are hidden. We hide the names of the variables. I like to label them at first so that near the end of the problem, I can refer back to them. Next up, we're going to talk about the kinds of operations we can perform on matrices, augmented matrices, in order to help us solve systems of linear equations. Next time.